Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. So I'd like to start off our event today by thanking MariaDB for sponsoring today's event. MariaDB is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, today's webinar is entitled Analyze Data Faster with an Open Source Columnar Database, and that'll be presented by MariaDB. But before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We have one presenter who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and today's event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Thomas Boyd with MariaDB. Now, Thomas is a Principal Solutions Engineer at MariaDB. He joined MariaDB in 2017 and brings with him 25 years of experience in the IT industry with a focus on databases and data storage technologies. Now, prior to MariaDB, Thomas worked at Oracle, Hewlett-Packard, and MongoDB, as well as with smaller startups in the Bay Area. So, Thomas, thank you for being with us today. We're looking forward to your presentation. Now, if you're looking for the scalability and performance needed to support interactive and ad hoc analytics on billions of rows, and with SQL, this latest Data Science Central webinar will show you how to combine distributed columnar storage and parallel query processing with powerful aggregate functions to deliver faster time to insight using modern on-demand analytics, as well as how to leverage the power of Kafka and Spark connectors to plug into existing pipelines. Now we'll discuss the architectural overview of columnar databases, share real-world use cases, and give a live demonstration. So Thomas, with that, I'm going to turn it over to you. You can begin just as soon as you're ready to go.
Okay, thank you very much, Bill, for that introduction. We wanted to start with a quick poll to understand where our audience is today with the kinds of technologies they're using for analytics. So if the audience could just take a second here and click on one of these choices here for the types of database or the primary database you're using for your analytics. That might be helpful in shaping a little bit of the conversation we'll have later on. So, sharing the results that we've got so far, it looks like we've really got a lot of folks on proprietary databases and more sort of mixed-use databases like Oracle, with a little bit of use of columnar databases in some of the audience here. Vertica was the example that we put here. So that's helpful to know, and we'll move on from there. So as Bill mentioned, we're going to talk about how to analyze data faster with an open source columnar database. And that database that we're going to be talking about today is MariaDB AX. So for those of you who are familiar with MariaDB and some of the core technology that it's based on, you're probably used to MariaDB as an OLTP engine, very popular, sort of the default relational database on most of the Linux distributions these days, and the backing store for a lot of OLTP systems, whether we're talking about the backing store for websites or enterprise IT systems like ordering systems or expense tracking systems. Maybe a little less familiar to folks is this other product that's in the MariaDB product line called MariaDB AX. In this case, the A stands for analytics. And what it really gives you is fast ingestion and analysis of large data sets. This is largely a data scientist crowd, so I don't need to talk about that much about why that's important. We all know the challenges of big data and sort of the challenges that organizations are having getting meaningful insights out of that data. And then the how of the way that we achieve this is it's a columnar-oriented database. We're going to talk a little bit about that format. It's distributed by default, so from the ground up, it's built to engage multiple nodes. And really, most importantly, and what distinguishes it in large part from some of the other plays we've seen in this big data space, is it's built on the widely adopted MariaDB SQL standard, if you will, or the ANSI SQL standard. So it differs from some of the big data or Hadoop-based approaches in that its birthplace is kind of coming from that SQL background as opposed to more of a just distributed file system. So a little bit about what we're going to talk about today. We're going to go through just an introduction of the architecture of MariaDB AX, and then we're going to spend a fair amount of time really talking about the adapters. So all of these big data solutions really boil down to two main things if they're going to be successful in the market. One is how quickly can they ingest data? How quickly can you put these large data sets into your 10 node or 100 node system? And then how well it integrates, how well you can query against that data once it's in there. So we'll talk about both of those aspects. So again, distributed built-in columnar storage. Once you have those multiple nodes engaged, it's really important that the parallel processing behind those nodes is able to support all the hardware that now can be engaged. It's not all that helpful for a big data system if the individual queries that are running can't be parallelized. And this is very different from an OLTP system, where in things like the flagship Oracle database or in the MariaDB TX, the core transactional engine, we've made optimizations that allow us to support many, many concurrent queries running. The more the optimizations in columnar database and in MariaDB AX are around having still a handful of queries running concurrently, but making sure that those individual queries that are asking to sort through large amounts of data can execute quickly. And that's really, there's a trade-off there that you have to make when you're building a database and a storage system for a database. So let's talk a little bit about the architecture. Core MariaDB server, whether we're talking AX or TX, has always had this concept of a pluggable storage engine. So most of the folks who are running that OLTP engine are familiar with the default storage engine called InnoDB. Very strong and mature storage engine, again, tailored for OLTP, right? So it has everything you would expect from an OLTP storage engine in terms of multi-version concurrency control, B-trees, locking, and all that. And we have always had this ability to drop in specialized storage engines for specialized use cases. So there's a memory optimized one for just doing in-memory operations on MariaDB. There's one that's really tailored called ARIA that's really tailored for read intensive, but still OLTP style reads where you're looking up singleton rows at a time, or small sets of rows, I should say. And so what we've done with column stores, we've taken advantage of that pluggable storage engine interface and used it in a clever way to, when you're writing to a table that's been defined as using the column store storage engine, it actually does a remote write out to another node, and that could be a physical node, it could be a virtual machine, or it could be a container that actually is responsible for storing that data. So there's really kind of two things that when I say column store, there's really kind of two big changes that are happening, and it's all happening through this pluggable storage engine that's always existed in MariaDB. One is the ability to kind of make this remote call and write the data on a separate node, and the other is the data format itself, and that's really kind of the crux of what a columnar database is, and we'll talk about that in a moment. So what you're seeing here on the bottom of this slide is that columnar format. If you're familiar with standard row-oriented databases, when you write a row, and in this case, we're looking at order information, right? So we've got an ID, the total amount that's been spent, and the name that's associated with it. This is obviously a very simplified example. In a regular database, that first line there of ID 1 and chain and a total of 50 would all be written together in the same location on disk, and also when it's pulled up into the processing engine, the memory area of the process of column store, you would be pulling up that whole row, whether or not you were asking to look at just one column or a couple of fields, the whole row would come up. What happens in a columnar storage engine is the data is organized differently, and we will take many, many rows and store all of the values for one column in a contiguous area on disk and then in memory. So that's the boxes around the data that you see here, where what we're illustrating is that all of the data for the IDs is going to be stored together in one. We can think of it as one file. It's really one set of files that could be spread across multiple machines, or set of files even on a single machine. And then there'll be another set of files that are storing all of the names in separate files. And this is really the core advantage of a columnar database. And it manifests in two different ways. The first way is because like data is being stored together, you can get much, much better compression of the data when you're writing into a columnar database. So oftentimes you'll find repeating fields. For example, if you have a field that indicates gender, those are only going to be two different values, very, very compressible. If you have text fields right next to other text fields, they'll generally compress well, likewise with dates. So you get this dramatic reduction in the size of the data as it's stored on disk, which has all the knock-on performance benefits of less data that you have to read from disk in order to get it up into memory and process in memory. The other real advantage is, and this depends a lot on query pattern, is that you don't have to pull every single column worth of data when you're looking at, if you really just cared about one column. So if I'm doing a query that really is just looking at, this total field and wants to organize it and maybe, aggregate it and sort it by one other column, maybe I'm doing some kind of a sales report that's going by region, I only have to pull the data from those sets of files that involve those two columns. Even if I'm doing a full table scan, which we should talk a little bit about indexing in columnar databases, even if I'm doing a full table scan, it's a vastly reduced data set that I have to look at when I'm only looking at those two columns. So it's those two knock-on benefits that have really made columnar databases very popular and powerful in the analytics space. In MariaDB, we have a kind of a naming convention for these two types of nodes. The first node, where MariaDB server is running, and that's where the SQL processing happens, where when a SQL statement comes in, it gets parsed. We do all the checking for permissions, or these tables that you're allowed to look at, and a plan is generated for which nodes it needs to go and execute and what operations it needs to execute on nodes. All of that's done in what we call the user module, or the UM. And then we call the storage modules the performance module, which I think that name sort of reflects that. This tends to be the really critical, performance critical node inside a MariaDB AX database that's been set up, because it's doing all the heavy lifting of reading off of disk. Most of the aggregations and computations that you're doing are going to be happening on these nodes. We'll do as much as we possibly can down on those PM nodes before the final aggregations and summarizations would happen up in the user module. So, of course, I mentioned that you can have multiple nodes, multiple PM nodes for storing the data, and that's what you're looking at here. And this is again critical to allowing that massive parallel processing, that you have all of these nodes. The point that I like to make is that, in fact, the operations, what we call the underlying primitives that are executing on these column store nodes, run in parallel even on those individual nodes. So it's not as if an individual query is limited to a parallelism that is 4 in this example, because I only have 4 PMs. No, in fact, that InnoDB server knows the computational power of the nodes that are lower down, and will pass off multiple primitives that can be run in parallel on each one of those PM nodes to really harness the power of what may be very large machines for these storage-bearing nodes. So that's why we have multiple arrows in this picture here. And of course, there is some work that's done in those user modules. Again, the higher level aggregations need to be summarized up in those layers, so you may need some scalability in that layer, and we would never want to have a single point of failure available, present itself in that UM node. So it's very common to run these large MariaDB AX implementations with multiple UMs. I will say that one thing that is not in this picture is data redundancy, and that's because it's really hidden from the user by and large. Each of these PM nodes, well, when you set up the system, you've been instructed to copy the data to multiple PM nodes, or in more detail, behind the scenes, if you have distributed storage like Gluster, where the nodes where the data can be mounted on multiple nodes, it has the possibility of mounting the data from a failed node up on one of the other PM nodes. So that's how we provide that data redundancy, is in the file system layer. And that's sort of natively integrated with column store. So there's an integration with Gluster if you don't have a preferred distributed file system that you're going to be using that will allow you to do that and get the data redundancy that you need for your analytics database. So bulk data adapters, right? So now we have this system that inherently wants to speak, wants to be interacted with through those nodes. And that's a great strength of this database. Again, it speaks standard SQL. You can issue the same insert statements that you were issuing against MariaDB, TX, our OLTP database, right against AX, and they'll work just fine. But those of you who are familiar with analytic databases know that oftentimes you want to do bulk loads, and you want to think about, what can you do to make the load process even faster. And in this case, it's especially important for columnar databases because there is a fair amount of work that has to happen on a per batch basis to take up that single row that you were inserting and break it up into those pieces and put it in those files, those columnar oriented files where the data is being saved. So all columnar databases make this trade-off where individual row inserts are going to be slower than you would have with an OLTP database, but as you can batch your inserts, because it's sort of a fixed cost to divide up those rows into those column-based files, you can get much, much faster imports if you're going in batches. And there are some other tricks we're going to talk about that can make it even faster. So lots of different sources for data that could be flowing into MariaDB AX, right? So you might have, standard data collection that's coming from applications and services, right? So maybe you've instrumented your website application and you have a whole bunch of clickstream data that you want to flow into a database where you can do analysis against it. That would be a great choice for MariaDB AX, or other kinds of sensor data that were coming from IoT systems out there, whether we're talking automotive or security. There's no shortage of data that could flow in, direct from the generating devices. There's also sort of a two-way relationship, I would say, between machine learning and MariaDB AX. Obviously, MariaDB AX is a great source for machine learning algorithms and data science that's getting done. We do also see those programs, whether we're talking about Spark or Python, running and generating results that might be used in further downstream analysis. So the idea that you're going to execute, a Spark job or a series of Python scripts to massage some data that may have come from MariaDB, but certainly needs to flow back into MariaDB AX is something that we see quite often. And then data imports, oftentimes some of these upstream systems are creating files that we're then going to be importing, and we have a set of tools to help you with that. So one of the real tricks, or the next level trick, we talked about inserting in batches, but the next level trick to getting bulk ingestion to run faster is to really figure out a way to engage the parallelism without letting that node, which is a potential bottleneck, get in the way. So I mentioned you can do your inserts, you can do your deletes, you can do your updates, everything like a regular SQL database through those nodes. But when you've got 5 terabytes of data that you want to get into the system as quickly as possible, what you want is this ability to push right from your source and directly right into those PM nodes. And that's really what the bulk data adapters are all about. You can have this set of rows that you make calls to do inserts on, but behind the scenes, it's bulking them up and making its own decisions independent of the about where it's going to drop, where it's going to create those rows and drop those files onto all of the PMs. So if you will, the bulk data adapters are sort of aware of the underlying topology of the MariaDB AX database and are able to do this bypass to make things run more quickly. Also, when you're talking about bulk data ingestion, the core pieces, the software itself, every single operation that you're doing in the software counts. And absolutely any extra copy of the data that's going to happen, for example, from, the core representation in C and then re-representing it, or a core representation in Java and then re-representing it somewhere else before you ship it off to those downstream PM nodes could be costly. So our approach here is that we have written all of these adapters, that the core software development kit for the bulk data adapters is written in C++. The compiled C++ is the fastest we can get it to run. And then we use Swig to integrate those libraries with Java and Python at this point. And we're looking at other downstream systems or programming environments that we'll integrate with. And again, here I'm just talking about the data ingestion. We're going to talk a little bit about I'm talking about language data ingestion. We'll talk a little bit about how things work with Kafka and Spark and some of the other options. So that those core adapters have, or the C++ implementation has 3 core classes: a driver that handles the connection management, a column store bulk insert core class, which is really the meats of the adapters. It's for writing data on a per table basis, and the ability to query the system catalog. So getting table metadata about where the data lives, what the table column definitions look like, et cetera, et cetera. And I mentioned that we're exposing these in Java and Python. So these are just the namespaces that you would use, whether you're programming in C++, Java, or Python, to access these core bulk data adapters. So here's an example of, in each of these languages, of invoking the libraries and then just creating a driver, creating a connection, if you will, into those into the column store database. In this case, the connection information needs to be stored in an XML file that lives on your system, and so that's where you see that little file reference happening there. Here's an example of the actual execution of a bulk load. I'll talk about the Java one on the right-hand side. So, we're initiating this bulk insert, and then we're on a row-by-row basis loading the data in and calling that write row, which doesn't mean that it's immediately getting written. There's batching that's happening behind the scene based on that bulk commit that you're doing. I should mention that by default, there's an auto commit set with these bulk loading SDKs, and I believe it's every 100,000 rows the data will get committed, but you may want to do it more frequently or turn off that auto commit and do your own commits. So pretty straightforward. Again, this is engaging that batch insert that's going to allow you to get data in much, much faster. This is an example of Python as well, essentially doing the same thing. Pretty straightforward. A few things to know. So these are really constructed for single tables and sort of doing, a batch, a single transaction batch at a time. You can create multiple instances and have multiple imports running at the same time, but there is a per storage node, PM node lock that's happening when one of these is up and running. So you'll only have one of these bulk loads running at a time on any given storage node, and it does this column store table lock that holds that. Right now, we're working on cleaning up what happens if you fail to commit or roll back. You just should be aware that there can be a table lock that needs to be manually cleared with an admin command inside column store. There is also a get summary call that can be made in all those languages that will return you some of the details of the load process. this is an example of pulling metadata from from C++ and Java using the bulk data metadata queries, looking at the system catalog table to pull information that you might need. Again, important that your program is able to interrogate the data schema and the setup of the database so that you know that you're importing data correctly. And an example of Python as well. So I want to talk a little bit about the Spark connector as well, and that's the next topic here. I kind of already mentioned this. So we do see a lot of publishing of machine learning results from Spark going into Column Store. And if you guys are familiar with Spark, sort of the core, the core data object is a data frame. And so it's really all about taking a Spark-defined data frame and saving it down into Column Store. And this can really allow you sort of a best-of-breed approach. So there's a lot of capabilities inside MariaDB AX in terms of, again, standard SQL queries and advanced analytic functions. So whether you're doing standard deviations or windowing functions or simple group bys, all of those kinds of things can be done in MariaDB AX and are probably better done there, where you can get the processing really close down to the data and let the core engine do it, and it does the massively parallel processing. Spark is great for higher level machine learning when we want to pull the data in memory into Spark, maybe have multiple passes across it and multiple aggregations that we're doing. And after those are done, you've often created a set of results that you'd like to publish back into AX, and so, or into MariaDB AX. So that's what we're talking about here. Right now, we don't have a bulk read API that's been exposed that you can use in Spark. So that said, you can, again, always use standard SQL. So there's a JDBC connector that works quite well with Java, and it works so you can just connect to us as you would with any other database in Spark and pull your data up that way. There are some additional jar files that need to be added, and we have a Docker image that's been published, which I'll show you a little bit of today, kind of as the quick and easy way to get at MariaDB AX and Spark and use them together. So I'm going to show you right now that Docker image. So if you'll bear with me, I'm going to share my screen. So what you're looking at right now is the MariaDB Corporation GitHub. And we've made a big investment over the last really half year in exposing as much as we can in these easy to consume GitHubs and ultimately Docker files. So if you go to MariaDB Corporation and then MariaDB Column Store Docker, that's where you'll find the starting point for easily running these things inside a containerized environment. Inside here, you have a couple of different options. I'll go up one level. So if you're just looking to run Column Store by itself, underneath this Column Store folder, you have two different sets of instructions for doing that. You can simply run a single instance of MariaDB AX. And I should mention, you will have noticed I've used MariaDB AX and Column Store interchangeably from time to time. Column Store is really the underlying storage engine. MariaDB AX is the product. But in case that confuses you, you can just sort of think of them as synonyms. So we do have a Docker setup that allows you to run it all inside one container, right? So it's inherently sort of suited for these distributed environments, but for a lot of testing purposes, and actually even for production purposes where it's a small data set, you might be running just on a single instance. And these are the instructions for doing that. I should mention that when you're doing this, you're pulling directly from Docker Hub, where we have also published the images, the Docker images that it's pulling down from. Docker Hub tends to be a little bit confusing if you're out there having a look. The one thing I would just say is if you're on Docker Hub, the place you want to be at is Docker Hub /u/MariaDB. So that's MariaDB Corporation's account. There are a few other community-built things and garage projects that are using MariaDB AX and the OLTP engine, but the stuff that we build and support is underneath this. If you see our little modernized icon here or logo here, you'll know you're in the right spot. So pretty easy to do that. There's also inside this column store location, again, the subdirectory under the column store Docker of column store. There is a quick and easy Docker Compose, set of Docker Compose instructions to run a setup that has 2 PMs and 1 So you can follow those pretty easily. I'm not going to demo those. You have a fair set of controls in terms of setting up, as you create this, setting up default users and default passwords, et cetera, et cetera. It gets a little more interesting, so we wanted to give people even more of a bootstrap if they want to do some meaningful work with Docker. And we have a couple of other Docker Composes that set up a sandbox environment where you can play with a bigger installation that has some data preloaded. And the MariaDB Sandbox one is a 2 2 PM with some fake data loaded from a fictional bookstore. And then the Jupyter one and the Zeppelin one, as you can tell from the names, use the BI tools or the notebooking tools, Jupyter and Zeppelin, for investigating that data. And so we'll take a little look at the Zeppelin one today, which also leverages Spark to do some of its queries. So I have that environment up and running. The way, again, the READMEs inside this GitHub give you all you need to know to get it up and running. Again, it's just a series of either building or pulling the images, and then we have a simple Docker Compose command that you can use to launch it. So that's if you pull down the GitHub and you do Docker Compose up build right from that Zeppelin directory, that will spin up all of the nodes that you need to have up and running. So again, in this case, we've got 2 UMs, 2 PMs, and then a separate container that's up and running with Zeppelin, with a predefined notebook, and with Spark running on it so we can do these queries. So that's what I'm going to show you right now. After you've done this Docker Compose up, you have the ability to go to, again, I'm running here on my laptop, to port 8080 and pull up this predefined notebook of queries that you can run against it. So I wanted to walk through that a little bit. If you aren't familiar with sort of this notebooking style, I grew up before we had to explain everything sort of in code right in front. And I think it's a really great way to make data science more consumable and meaningful, and it lets people inspect and understand what's happening underneath the covers. But you can see here there's a definition of preparing the database connection that's been executed, so we know that it's running. We can fetch information, so you can see right here, inside the notebook here, what we've essentially said is, here's the database query that we want to execute to go down and pull transactions from our, in this case, we're pulling from the loyalty points and a couple of other tables as well. We're pushing those into a data frame, so that's this DF here. So when we run this read JDBC, we're publishing it into a data frame. This call here is what says, hey, take that data frame and publish it back down into MariaDB in a table called stats. And then later on in this notebook, you can see us querying against stats. Or the data frame exists in memory inside the Spark execution environment. So again, you always have this choice of, well, do I want to go and execute a raw SQL query against the database, or do I want to get everything pulled up into Spark and run it as a Spark job and do some machine learning through Spark that way? So that's what that looks like. This is sort of self-explanatory, so you'll find these notebook entries that really don't have code, but just document sort of the flow and what we're trying to illustrate here. This one here is an example of a direct run SQL statement. So that's this #SQL. Earlier on, we defined the connection information. So again, the password and the port that we're connecting into. One of the nice things about Jupyter is you have these different ways of displaying the data sort of at a click of a button. So this is the table layout of just simply selecting the number of rows from this stats table. And again, in the stats table is where we've loaded up the row counts of all these tables. But if I wanted to display it as a bar chart or a pie chart, all that's available. Just a couple more things I want to show here. Here's another example of a push down query, and it's a very simple one, right? So we're defining this push down query and then saying, hey, please build a data frame called books that just executes this query. And it also has some schema information about the way it's going to represent the data that gets pulled into there. A few more simple queries. You can, from Zeppelin, when you're executing a Spark job, you can drill down on the Spark job and see the details of what's happening there, get into the Spark execution environment. That's what this tab is showing right here. And the last maybe couple examples that I wanted to show from here are, again, we're trying to have this interactive and defensible data exploration, where we started just getting a raw number of the counts of books. Now we're doing it by category. Now we're doing some analysis on, I don't know if I would really call it profitability, but just looking at the average price of the books and where we think there's the most money to be made. And then we're comparing that with where we're doing our most of our sales. And then a breakdown of our customers by age over here on the x-axis, and the y-axis is a stack of their marital status. So lots of different ways, and again, you've got this choice, this nice integration. If you're used to using Spark, when you've got a data frame where you've massaged all your data and you want to push it down into a table, it's really as easy as that one call that I showed where you're doing that create or replace table, just right straight from a data frame. I think maybe at the very end here, we have some more interesting graphs. And let me show you, here's an example of just working directly with one of those populated data frames, right? So I had already queried the books table and loaded it into this data frame called books. Now, if I want to execute a Spark filter on top of that, I can just do this and filter it by fantasy and order by that, and ask the Zeppelin, so Z is the Zeppelin execution environment, to show that. And that's what gives me this nice little widget here that allows me to show it in many different ways. So Spark is getting used in a lot of different places. I just felt like, and we felt like when we were building this sandbox environment, that this was a really nice way to expose it and let you guys have a graphical interaction quickly with some data that's both in Spark and inside MariaDB AX. So let me go to the next screen, stop my sharing. Again, just some pointers on how to get this up and running. The local host on here might be incorrect. It's actually 8080 now in the current version of that GitHub. So a little bit about streaming data adapters. So this is all about pulling things from Kafka, I would say, is the one that we're seeing a lot here, where there's a topic where we're using a pub sub queue like Kafka, and we want to get the data into MariaDB AX so we can start to do the analysis on it as quickly as possible. And it's obviously leveraging a lot of the stuff that we've talked about before. The one thing you should know is this is, you can think of it as a pre-built adapter, right? So we have these SDKs that are Java-based and C++-based and Python-based, but we have a working piece of software called MariaDB MaxScale that can run in this mode where it's acting as a change data capture adapter. So, well, and the one we're talking about right now is streaming data out of a MariaDB TX install. So we've got our transactional database that's up and running, maybe backing a web store or something, and we want to flow that data into our analytics database. And so MariaDB has always had this replication capability where as data changes in the database, it's written to a bin log. We've exposed a separate thing, if you're running with MaxScale, that gives this CDC list of what changes have been happening in the database. And so when you're running MaxScale to watch one of these OLTP databases, it produces this nice consumable stream of activity that tells you the changes that have been happening on the database. You can also, instead of coming from a MariaDB TX database, you can subscribe to a topic in Kafka. And again, you'll be running that streaming data adapter, that Kafka streaming data adapter, and it's using all that bulk stuff that we talked about the SDKs to just take what's presented by Kafka and write it down direct to the PM nodes. So you get the kind of performance that you need for these very large Kafka topics. So it's really as simple as, saying which topic that you want to subscribe to and where you want to publish that information into MariaDB AX. Okay, so we're getting near the end. Let me give you a little help here with the Kafka adapter. So getting started with that, this is the place you want to go for that. Again, it's expecting to read Avro formatted messages from Kafka. So there's lots of details there. Just a real quick look at sort of the big picture. What does it look like when you've got all of this together? We've all got these really complex IT environments now, right, where we have data that's coming from multiple locations, and we want to be able to get all of that into the data warehouse style application, MariaDB AX. And so whether it's coming from, maybe direct from some services that are running, you've got something in your application tier, a service that's running, you want to direct log information from there into MariaDB AX, you can do that. Maybe you have some stuff that's coming from Kafka, or you have some stuff that's coming from the back end of your OLTP system. That's what we're looking on the left-hand side there. And then you've got this two-way communication between analytics passes that are happening, whether you're using Spark or Python or other machine learning and data science approaches, where you want to be able to easily get at that data, massage it, and put it back into MariaDB server so other people can take use of the insights that you've generated. So these quickly grow to pretty complex environments, but we feel like we've got the right pieces here to allow you to integrate these without too much of your own elbow grease, right? So it's nice to have that Kafka adapter where you can just subscribe to a topic. It's nice if you've written your services in Java that you've got a really clean API for doing bulk, fast inserts. So that's it for the formal part of the presentation. I will hand it over now to Bill, who's going to moderate the question session. So I'm looking forward to hearing some questions from you guys.
Well, Thomas, thanks for that excellent presentation. So we'll get started with today's Q&A. And I want to thank the audience for their participation. We've had a lot of questions that have come in, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen with contact information with Thomas, if you'd like to contact him following today's event. So let's get started. Thomas, first question from the audience. How does MariaDB AX compare to other Columnar databases?
Sure. Good and very practical question. So I would say it's very different than the whole class of SQL processing that's been built on top of Hadoop. So I think we've seen multiple fits and starts of how to get SQL-like processing to run on top of HDFS. And by starting with a proper relational database with an optimizer and a parser, we've been able to be much faster. And the data itself is also inherently, stored in a format that's tailored for our engine to execute its primitives. The net of that is it's much faster than the Hadoop-based systems. It would be similar to the proprietary columnar databases that are out there, like Vertica, for example. And I think that if you're using Vertica, I think we're seeing more and more people looking to embrace open source and some of the flexibility that you get out of that and moving to AX.
Well, okay, thanks for that clarification. I think you probably just answered the next audience question, which is, can I actually write the code in R?
So yes, you can. There may be a little more elbow grease there. I'm actually not sure of the current community adapters for writing in R. But in general, you have these SDKs that you can use to kind of get to the underlying primitives of doing these bulk inserts and writes. So it just may be a matter of a little more elbow grease to get that done.
Okay. Well, thank you. Now, we obviously focused on AX, the analytic version of the database, but obviously MariaDB has a transactional database. and of course it's a data science audience, but the audience is wondering, well, if you handle both OLTP and OLAP, is it primarily tuned for analytic or primarily tuned for transactional?
Yeah, great question. So remember, we have those two separate product lines, and they do overlap a little bit, right? We're all working in sort of these hybrid transactional analytical environments now. But the core strength of MariaDB TX is OLTP style applications that are usually write intensive, and then the reads that are happening tend to be on smaller data sets, often retrievals of individual rows. MariaDB AX is the one that's tailored towards analytics. Now, lots of people, especially on smaller data sets, are able to run a fair amount of analytics right out of their core OLTP database. And if you're not bumping up against performance constraints, that may be just fine for you. It is also possible in one installation of the product to have a mix of tables, some that are using the standard InnoDB storage engine and some that are using the Columnar storage engine. That works, again, in some use cases, but sometimes, especially if you have a heavy analytics workload, it may be best to have them separated into separate clusters.
Okay, that makes perfect sense. And while we're on the topic of resources, the audience is wondering, is this primarily an application that should be used on-prem or hybrid or cloud or all of those?
The short answer to that is all of those. We have lots of people running in public clouds, AWS and Google Compute. We have many people running on-prem. It is software and able to run even in containerized environments, as you saw today.
Oh, interesting. Okay, thank you for that answer. Now, a couple of interesting questions about how much control the admin or the user has over the operations and how much of this is basically restricted to what MariaDB has to decide on your behalf. So the question is, do I have the flexibility to create a table that's totally stored on memory and control where it could be written on disk or vice versa?
So you probably don't have as much direct control as you're asking for there. There is, behind the scenes, these files that are getting created are essentially loaded in the order that the data is loaded in. And so for certain kinds of queries, if the order that the data was loaded in is advantageous to those queries, there's a pruning process that is kind of what you're asking of the partitioning of the data, right? So you will see this strategy where sometimes the data, at least in the small batches, is purposely ordered. And maybe it's coming out of the source systems ordered anyways before it's put into MariaDB, because that load order becomes important and is essentially the way that the data gets partitioned, and most importantly, the way that it can be selective about where it has to go to answer certain questions.
Okay, and then this would be a similar or follow-on question. Does the user have the flexibility to choose the key and the strategy for partitioning data so that the cluster would know in advance where to look for the submitted key query?
Right.
Or is it
right.
Just automatically pushed out across all nodes?
Yeah, and so the short answer to that, well, there's two answers. One is you can declare, if you had something that was relatively small, again, you could declare it not as a column store engine and store it, it actually would get stored up on that UM node, and that makes it accessible to everyone who's querying through those UMs. The partitioning that happens, again, it's just going to take there isn't a defined key. MariaDB pushes it out, if you will, blindly, and sort of the way around that is to give it to it in a sorted order that's going to be most meaningful for you. So if you have a particular key that you wanted your primary access pattern to be on and to have efficient pruning happening for that, then you would sort your batches by that key before you dropped it in. And there's actually some good reasons for that. It's a little bit of a waste of database resources to have the database essentially do that sorting and get in the way of other queries that are happening. It's something that we're leaving it to you to be able to do out in your, again, out in your application land in the import space as opposed to in the core database engine. There's some performance benefits to that.
Well, okay, thanks. That makes perfect sense. Here's an interesting question about the backstory, I guess, from MariaDB, and that is MariaDB AX the former InfiniDB?
And the short answer to that is yes. So InfiniDB had a long history, but we really felt that taking them kind of underneath us and taking the good work that they had done and making it a fully supported part of the MariaDB offering was the right way to bring this to market for the customers who were really struggling with these analytics problems. But the short answer is yes.
Oh, interesting. Oh, always good to know the history. Are there particular kinds of data models or queries that work particularly well on MariaDB AX, and conversely, are there those that don't work particularly well?
Sure. And this is going to be really the same answer for all distributed databases, which is data models that are going to force a lot of joining. So, 3 and 4 layers deep are going to struggle in distributed databases because they end up having to shuffle a lot of data around between different locations. So we work very well with the standard star and snowflake schemas that you see in in data warehouse modeling. We also work relatively well on, if you will, not horribly nested OLTP models. So we have a lot of people who publish their OLTP model straight into MariaDB. They use that change data capture tool and just push everything into MariaDB AX and get all the benefits of columnar storage. It will break down if you've got that massive query that's joining, 5 or 10 tables and it's got some subqueries in it. Those will give us problems, which is true of just about, really of all distributed databases. And that's where maybe some massaging and some modeling into a snowflake schema or a star schema is required.
Yeah, I guess you could make anything too complex.
Yeah.
So we talked a little bit about on-prem and cloud and that sort of things. What are those sort of minimum or typical compute resources that you need to run MariaDB AX?
Yeah, so that's a really good question. One of the customers that was always surprising to me is there's a IMHE, which is a non-for-profit that's doing monitoring of health data globally, had a really interesting problem that I wouldn't have thought of as being a great solution for a great use case for AX, where their folks were out in the field wanting to demonstrate the analytics they could do. Actually, the pages that they have look a lot like what you saw in Jupyter there. Or sorry, I was showing Zeppelin, where they're showing bar graphs and slicing and dicing the data different ways. They're in sub-Sahara Africa, and they want to talk about that. And they had to do this all off of relatively low-powered laptops, and it was a big data set. And they ended up switching from an OLTP database to MariaDB AX and are running it on single laptops for this use case. It is also the backing store for their website. So it can run, and there are use cases for it to run on single node machines. Again, if you've got those queries that are just looking at one column, and unfortunately you have these rows that were really big and rich, you're going to see a really big performance gain. That said, it shines, when you've got that data set that's in the, tens of terabytes or hundreds of terabytes, and you're spreading it out across, 3 PMs or 10 PMs or 100 PMs. That's really its sweet spot.
Oh, that was really interesting about that, using it on laptops. That's remarkable. Back in your presentation, you talked about the max scale application. And the audience is wondering, okay, so when I'm bringing data in from MariaDB transactional TX, does MaxScale have to replicate all that data into MariaDB AX, or is it selective in some way?
It's selective, so you can filter on a table by table basis.
Okay, all right. Well, hey, Thomas, thank you for some great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll send all the unanswered questions to Thomas and the MariaDB team so they can follow up with you after today's webinar. I have just a few quick announcements. If you'd please mark your calendars for January 22nd, and that's our next DSC webinar, which is Data Wrangling and Automated ML, the Consensus Story. So also remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Also, our previous webinars are available on demand at Data Science Central, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Well, this brings us to the end of today's webinar. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to MariaDB for their sponsorship, and particularly our speaker today, Thomas Boyd, for his insight into today's topic. This is Bill Vorhies. I'm very pleased to have been your host for today's event. Look forward to seeing you all again on January 22nd. Have a great day.